Hi there, and welcome to a new episode, episode 4 in the Geology 101 Physical Geology video series. I'm Geology Professor Shawn Willsey. Thanks for joining me today. Today our topic is going to be on convergent plate boundaries. This is the 4th episode in this video series, and this video series has been set up for those who might be interested in learning geology for the first time ever in a semi-formal setting, or for those who've maybe had classes in the past and looking for a refresher. Anyone who's interested in geology, all are welcome. So thanks for being here. This video series is modeled after my college courses. It's the same lecture material, the same content that I would present to my class. The only thing missing, of course, is the field trips and labs, but you can somewhat supplement those here as well with some of the other videos in my catalog. So I encourage you to please look through those, and you might find some topics that are relevant to the particular topic you're interested in. So let's go ahead and get right to it. So in our last episode, we focused on our first plate boundary type, which was divergent boundaries. When when plates move apart and magma is generated, we called those constructive plate boundaries. Now we're going to look at what happens when two plates collide, when two plates actually run into each other, or what we call a convergent plate boundary. So this is a collisional area between plates. It's a destructive plate boundary where we are going to recycle and remove older crust from off of the Earth. So it's in contrast to those divergent plate boundaries we learned about last time. And it's a little bit more involved here than a divergent boundary in the sense that it really depends on what kind of crust we're dealing with as to what exactly takes place. So we know that we have two types of crust on planet Earth. We have oceanic crust, which is heavy and dense and relatively thin and primarily made out of a rock type known as basalt, a dark volcanic rock. And in contrast, the continents are mainly composed of a different rock type, granite, and that's what continental crust is. And granite tends to be low density, quite buoyant, and much thicker. And so depending on the types of plates involved, that's going to dictate to some degree what sort of scenario is set up. And so we'll look at each one of these. We'll look at the situation when two ocean plates collide, when a continent and an ocean plate collide, and then finally when two continental plates collide. So let's go ahead and start with our first situation where we have two oceanic plates colliding. The process here, and we're going to use this term a lot, not just in this video, but probably in future videos as well, because it's a very fundamental process on planet Earth, helps us understand volcanoes and earthquakes much better. This is a process known as subduction. So when two ocean plates collide, one of those plates is going to sink or slide beneath the other. And the process of one plate descending beneath another is this process we call subduction. You might ask, well, who's to say which plate is the subducting plate? What determines or dictates which plate is actually the downgoing plate? And we can answer that by comparing the two ocean plates that are involved and seeing what their ages are. Remember that ocean crust is generated, as we learned in the last episode, at a divergent plate boundary. So as these two plates come together here, the ocean crust or ocean plate that has the oldest age and therefore is the most dense and heavy, that is the plate that is most likely to sink and subduct beneath the other. So whenever we look around planet Earth and we see these subduction zones and we get age data on either side of that subduction zone, we see that universally that the ocean plate that is oldest is the one that subducts and sinks beneath the other. Even though they're made out of the same rock type, there's enough of a difference in their densities due to their ages to cause one to sink beneath the other. When one plate dives beneath another part of the process, another characteristic we see is that magma is generated. We'll talk about this more when we get to igneous rocks, but for now, let's just leave it fairly simple. And that is that as the ocean plate slides down, water is driven out of that downgoing plate. It reacts in the asthenosphere on the plate that's riding above the subduction zone. That ocean water is reacting with the asthenosphere, causing some of it to melt, generating the magma. The magma is buoyant and less dense than the rocks that it is residing in, and so it tends to rise. And of course, when that magma makes its way to the surface, it ultimately creates volcanoes. And in this case, what we're going to see is a chain of volcanoes forming what we call a volcanic island arc. On a map, these tend to be curved in map view, partly because of the Earth's shape as a sphere. And so this is some of the characteristics we see here. So a subduction zone, we sometimes call this region where one plate's diving beneath the other, a subduction zone. So that's kind of the phrase we use for this overall tectonic setting. The magma being generated here. We see some of the Earth's largest earthquakes happening in subduction zones, upwards of magnitude 9 in some instances. So as I think back to the last big earthquakes in my lifetime that I've been alive for, I think of the Japan earthquake in 2011, which was around magnitude 9. The Sumatra earthquake in 2004 was a little bit over magnitude 9. So this is the type of plate boundary that produces our largest magnitude earthquakes, which is something important and something we'll circle back to when we talk more about earthquakes later in the course. The other thing we see as a characteristic feature of these ocean-ocean convergent zones is right where this downgoing plate starts to bend and dive into the Earth. As it's flexing and diving in contact with the other plate, we get a narrow, deep ocean trench right along the plate boundary. So this is where we see the deepest portions of the ocean floor is right along these trenches that mark these subduction zones. And there's lots of examples of these types of plate boundaries. I've listed a few here: Japan, the Aleutian Islands, Indonesia, but there's others as well. And it might be a fun exercise for you to just pull out a map that shows, or get on Google Earth even better, and see if you can find where some of these subduction zones might reside, just given some of this information and these characteristic features we've talked about here with the magma, the volcanic island arcs. You obviously won't see the earthquakes on that type of imagery, but you can pick out those deep ocean trenches. So this is ocean-ocean convergence. When we take out one ocean plate and swap it out for a continent, we see actually a pretty similar process with just a few small differences. So we still have that deep ocean trench. In this case, there's no question as to which plate is going to be subducted or forced downwards. It's going to be the ocean crust because it's so much more dense than this buoyant and thicker continent that it's running into. And so the ocean crust subducts. We still get the magma being generated. So in this case, instead of getting a volcanic chain of islands, we'll have a volcanic mountain chain on the continent. So notice that the volcanoes are preferentially on one side of the subduction zone, on the plate with the overriding plate on that side of the plate boundary. We still have our deep ocean trench. We would still have very large earthquakes along this subduction zone. And then just a few examples here as well. The Andes Mountains, the Cascade Mountains of the Pacific Northwest are good examples of these, but there's others as well. Those are some of the more classic examples of that type of plate boundary. Moving on to our final convergent plate boundary. Well, what happens when we have two plates made out of continental crust that collide? So in this case, it's a little bit different. Actually, it's a lot different. We have two plates made out of buoyant continental crust. Now, we might get some initial subduction at this plate boundary if there's a leading edge of ocean crust. So in this particular diagram here, they are showing subduction because there was some oceanic crust. But once these two crustal masses come into contact, that will end subduction. The continental crust will not be forced downwards appreciably, and we will no longer have subduction, so we no longer have magma generation and volcanoes for the most part. Now you can get some magma forming here as you thicken the crust, but the classic model of magma generation by subduction doesn't apply to this type of plate boundary. This is sometimes called obduction, which is kind of a funky word and isn't used a whole lot, but is a little bit more succinct and kind of matches up with subduction. So subduction and obduction. So as these two continental plates come into contact and are continuing to move towards each other, that of course results in very high lofty mountains. They're both made out of buoyant crust, so instead of things being pushed down, the low density of the crust causes the mountains to be pushed upwards. These rocks are highly deformed at depth where they're somewhat more flexible and easy to bend. We might see spectacular folding in the rock. We also might see rocks breaking and being pushed past each other, which would be faulting. And so we see a lot of earthquakes as well with that type of plate boundary. So no volcanoes typically, but big mountains, rocks that are deformed, and these areas can also produce large earthquakes. Not as large as a subduction zone, not into the magnitude 9 range, but still devastating earthquakes well into the magnitude 7 range. And then the two sort of classic examples of this in our modern period of Earth's history would be the Himalayas, where India has plowed into Asia, and the Alps, where the leading edge of Africa is actually plowing northward into southern Europe. Okay, so those are our examples. And oops, let's not give away the question just yet. Let me show you a few Google Earth examples, and let's go explore some of this on Google Earth and check out some of these plate boundaries. So what I've done here is chosen 3 different areas that I feel represents each one of these plate boundaries pretty well. So let's start with an ocean-ocean convergent plate boundary. And for this one, what we'll do is head out to the Western Pacific. Here's Indonesia, Australia, Japan's right here. And this is the Marianas Trench. So this is the deepest part of the ocean on planet Earth. And on one side of this trench, there's a series of islands, the Marianas Islands. Most of these are volcanic in nature. So I drew this line right through one of the islands and right across the trench. And what we can do here is look at the elevation profile across this area. So as we move from, well, I guess I've got this a little bit backwards here, but that's okay. But we'll move from east to west, and you'll see that as we move from east to west, the elevation of the ocean floor gets deeper. It maxes out right about this point at the trench, upwards of 9 kilometers almost in depth. I did switch to metric for this, so apologize to my English unit folks, but you can easily convert back and forth. So down to 9 kilometers here. And then as we leave the trench, of course, we're on the overriding plate. So the plate boundary is more or less marked by the location of the trench. So this, in this case, on the east side is the Pacific plate, and then we have the Philippine plate over here. So as we move to the west, we're on the Philippine plate. And once we get some distance, usually a couple hundred kilometers in this case, away from the plate boundary, we have the volcanoes. You can see where the actual volcano and the island sticks up over here. We can go ahead and zoom in a little bit and actually see that, yeah, that looks a lot like a volcano crater at the top. Later we'll talk about volcanoes and what type of volcano this is and how explosive it is. But there's a nice little cross section through an ocean-ocean plate boundary with these exceptionally deep ocean trenches marking the location of that plate boundary. So there's the Marianas Trench. If we go to the Andes Mountains in South America, I have a cross section here through the plate boundary, the subduction zone that lies here. Again, on Google Earth, these trenches show up nicely. It's got the, we have the depth of the ocean shown in various shades of blue. Lighter blue is more shallow, and deeper shades of blue is deep. So if we come down here to this cross-section line and look at, in this case, this one's oriented a little bit easier for you. So this is from west to east. So we'll start over here on the west side. We're on the Nazca Plate. So the Nazca Plate is an oceanic plate, and this plate is in collision with the South American plate. So you can again see where that trench is designated here. Here the trench is almost about 7.5 kilometers deep, and so another deep ocean trench, a little narrow zone where the ocean floor is quite deep. And then as we move to the east beyond the trench, we are moving on to the overriding plate, which in this case is the South American plate. And then we get onto land here, and then it finally rises up to this high point here, which is a little less than 6 kilometers above sea level. And if we zoom in there, of course, remember we should see volcanoes on one side of the plate boundary. And sure enough, there's another landform that looks a lot like a volcano. Another one here, probably another one there. And you can move up and down in a north-south direction along the coastline here in a certain distance inland and trace out the location of these volcanoes. So these volcanoes that exist in the Andes throughout Chile, Bolivia, Argentina, Peru, are there because of this subduction zone, which pretty much runs the entire length of western South America. And then finally, our last little profile view that we'll use Google Earth for is to head over to a place where there's continent-continent collision. So in this case, we'll go to the Himalayas. So we're over here where India meets Asia. And as many of you know, this is the tallest mountain range on Earth. Mount Everest is in there. And the Indian subcontinent is still plowing into Asia, even though this collision began 30 or 40 million years ago. This collision is still going on, and so these mountains are still being uplifted. Lots going on here, but let's just check out our cross-section line. Let me see which way I've oriented this. And yeah, so this is oriented from south to north, so we could actually spin around this way. That make it a little more easy to understand. So we'll start out in the low elevation plains of India, just about 100 meters or so. You can see how flat it is on the topographic profile. And then as we approach the plate boundary, which is more broad, it's not as well designated by a trench. It's a bit more diffuse, but you can still see just over the course of a few tens or so of kilometers that the elevation changes dramatically, and that indicates, of course, where the plate boundary is. Looks like the highest point we get here is a peak that's somewhere between 7 and 8 kilometers in height, so over 7,000 meters in height. Pretty lofty there, these big mountains that are right along the plate boundary. If we zoom in here, of course, none of these look like volcanoes like we saw with the subduction zones. They're tall enough even at this relatively low latitude to accumulate snow, and many of these also have large glaciers on them, and so glaciers have modified this landscape quite a bit as well. And then as we move further to the north, you can just see just how high these elevations are. This is part of the Tibetan Plateau and this high elevation region that extends to the north. So this type of plate boundary is a little bit more broad and more encompassing of larger areas than we see with the subduction zone. But I thought the profiles would be a nice way to understand these three types of plate boundaries in a little bit more detail. So hopefully that was helpful there. And I'm just now remembering that I totally forgot to show you the animations that might help with these as well. So let's start with the ocean-ocean collision. And so here is the older ocean crust diving down to the right beneath the younger ocean crust. And so as we've learned here with the PowerPoints, that generates earthquakes. It also generates melt, which produces a chain of volcanic islands. So there's our chain of volcanic islands here, the trench here. We'll talk more about this word in a future episode. This is just where stuff gets kind of plastered into or onto this overriding plate a little bit here. So that is one of our plate boundaries, ocean-ocean. If we switch over to ocean-continent, we see similar sort of thing. So subduction zone, earthquakes, and magmas being generated that are feeding these volcanoes on one side. So this set of visuals might help some of you as well understand what's going on. And then here's our continental crust animation. So two continents moving towards each other, a little bit of ocean crust in between, which is initially subducted. So we can see there's some subduction initially. So we've got a subduction zone here, but eventually as these two continents start to collide, this subduction zone gives way to this other type of convergent plate boundary. And you can see how the whole area gets uplifted, the crust gets thickened. Again, all of this takes place over tens of millions of years with earthquakes, folding, all sorts of other processes that are occurring there as well. And then we get these big mountains there. So, okay, so let's now move over to, so we've done the PowerPoints, we did the animation, the Google Earth section. Let me wrap up here, and hopefully you'll remember this from the last episode. Remember the last episode we finished it up with a little assessment question, a quiz question. This is one that I give in my classes. This is actually the exact same question as the last episode, except instead of looking for the right map pattern for a divergent plate boundary, here we're looking for which one of these 5 maps, A, B, C, D, or E, best matches the earthquake distribution that we would expect to see from a convergent plate boundary between two ocean plates. So if you didn't watch the last episode, let me quickly explain. Each one of these letters is a map. The plate boundary is the dashed line going down the middle. The dots are earthquakes, the locations of earthquakes on that map. And the color of the dot corresponds to the depth of the earthquake. Black being shallow, blues and greens being kind of intermediate depth earthquakes, and reds being exceptionally deep. So the earthquakes get progressively deeper. So what you need to do here is figure out which one of these show the pattern we would expect to see at a convergent plate boundary between two ocean plates. I guess the big hint I can give you here, maybe to make your chances a little bit better of getting it right, is that when we looked at this last time for the divergent plate boundary, the answer was E. So this option here is the pattern of earthquakes for a divergent plate boundary. So I would encourage you to take that one off the table. So you got a 25% chance if you just randomly guess this, A, B, C, or D. The other thing to consider is, remember what we learned about in episode 1 about the layers of the Earth. Not all layers will respond to the stress at a plate boundary the same. Some layers will behave brittly and they'll break and they'll generate earthquakes. Others might not. So also remember that earthquakes are produced when stress is built up in rocks and the rocks break and shift. And think about where that might actually take place. So this is a good point now to pause the video if you need some time to sketch some stuff out or maybe look something up or think about it or have a conversation with a friend or a conversation with yourself. Go ahead and pause the video, and then when we come back, I will reveal the answer. All right, so hopefully you've had some time to think about it. We're going to go ahead and figure out the answer. So again, in review, A shows shallow earthquakes along the plate boundary, and the earthquakes get deeper to either side. B shows a mixture of shallow and deep earthquakes right along the plate boundary. C shows shallow earthquakes along the plate boundary, and the earthquakes getting deeper in one direction. And D shows deep earthquakes along the plate boundary, with the earthquakes getting shallower in both directions. And remember that the distance across these very small little cute maps is, let's say 1,000 kilometers or more. So they represent a substantial distance. So the correct answer to our fun little quiz question here is C. C is the correct answer for the distribution of earthquakes for a convergent boundary between two ocean plates. So what would it look like if we had two ocean plates colliding? Well, remember that is a subduction zone. So we would see one plate diving beneath the other. So in this case, I've set that up with my little drawing here. So here's the ocean, here's my pirate ship. We've got this plate here made out of the crust and the upper mantle. These are the hard, rigid layers that make up the lithospheric plates, the plates that are moving around on planet Earth. And they're sitting on a soft, squishy layer that is quite weak called the asthenosphere. So in this case, we have this plate moving to the right, colliding this other ocean plate, presumably of an older age, which is moving to the left. And what I've drawn here is the magma that's being generated with all this red. There's our little volcanic island. Here's the trench, lots going on here. And then the X's are where we might expect the earthquakes to be. So notice we have earthquakes in the shallow region here, but we also have earthquakes that get progressively deeper as we move from the plate boundary, which is at the trench, and we move in one direction, in this case over here. And they actually go off the page here. This subducted slab goes down literally hundreds and hundreds of kilometers down into the earth. And so we still have earthquakes happening at depth here because remember, this is a rigid tectonic plate. It is still made out of rock. And as it flexes and moves down and the other stresses that are on it causes rocks to break and shift, and that's what's generating the earthquakes here. So a lot of earthquakes are happening in the shallow region, but there's still earthquakes happening at a variety of depths. But there is a nice progression from shallow to intermediate to deep as you move, in this case, from the plate boundary to the left, and that matches pretty nicely with C, what we have over here. So last thing here is to maybe convince you a little bit more and show you the real data behind what I've drawn there. If you need something to decorate your house or your garage or your office, you could do a lot worse than this, and I'll put a link to this in the video description. This is the USGS beautiful map. This comes in a big, I'm trying to look how big mine's at least 4 feet wide as I look at my office wall here. It's a very large map, so don't let the online version fool you. But this has a lot of great information, and this is called this dynamic map. So if we zoom in, for example, to, let's say we go over here to the West Pacific, we can see what this map shows nicely, and one reason why I love this map so much is it shows several things. It shows the plates. The white arrows are the directions the plates are moving. The little number is their rate of motion in millimeters per year. The red triangles are the location of earthquakes, and the dots are earthquake locations. So what we can see from this map, if you know a little bit about plate boundaries, let me zoom back in a little bit, trying to find the right blend, is that the divergent plate boundaries, such as we see here in the eastern part of the Pacific, do have earthquakes, but not that many. The plate boundaries that produce by far the most earthquakes are these convergent plate boundaries, these subduction zones. So you can see them stretching from New Zealand up through the South Pacific over here, along Southeast Asia, up along the border of Asia through Japan to Northeast Russia, and then coming across the Aleutian chain into Alaska. Similarly, we can see more of these subduction zone earthquakes here in southern Mexico and Central America, and then most of the western margin of South America. So not only do these locations have the most earthquakes by far, they also have the deepest earthquakes as well. And so you don't see depth on this map, so I have another map here that will show this a little bit better. This is actually a map I use for an assignment that a colleague put together. So on this map, the red earthquakes are shallow. The yellow earthquakes are a little bit deeper. Then it goes green, then blue. So notice over here, like let's say in the divergent boundary that runs through the Atlantic Ocean, the earthquakes are only shallow, and that's something we learned from our last episode. But when we look at the subduction zones, like here in Central America or along the west coast of South America, notice you see a much more diversity and a bit of a organization to the earthquakes. Now, it's not perfect, but in general, looks like there's a lot of red earthquakes right along the plate boundary, right on that trench that's close to the coastline. And then there's crudely a band of yellow earthquakes, a little bit deeper. The greens tend to be a little bit further inland, further away from the plate boundary. And then we finally get to those ultra deep earthquakes. And so that's very similar to, and then look at this pattern over here that kind of went off the map on the other side of the ocean. Maybe we can go over there and check that out over, towards New Zealand. And so you can see these patterns here that show up pretty nicely with these subduction zones, especially here in the West Pacific. So the point here is that this distribution of volcanoes from shallow to intermediate to deep, as one moves from the trench where the plate boundary is towards one side, matches pretty nicely with the data that we see here, and also matches pretty nicely with our little quiz question here. So hopefully that it was helpful. Hopefully you enjoyed this little section in this episode on convergent plate boundaries. We will continue in our next episode with our third and final plate boundary type, and that's transform plate boundaries. I'll probably also in the future do a little bit more of a deeper dive on plate tectonics. Some of you who might know more about plate tectonics are wondering, why hasn't he talked about accretionary wedges and ophiolites and all sorts of other things. But remember, this is a Geology 101 course. We're just starting with the basics and a good fundamental understanding, and then in future episodes we'll add to that. So thanks again for joining. Appreciate your support of the channel, whether that's financial or just whatever support you give, and we'll see you at the next episode. Take care and thank you.